Now let us try to find the second solution to this homogeneous differential equation. Homogeneous because there is a 0 on the right hand side. What is our expectation? We have the first one, e to the rt. We know this is the solution. And the second solution is a multiple of it, but it is not just a number multiple, integer multiple, but instead it is multiplied by an unknown function of time and then x1. So that x2, the other expected value, the expected function is v of t and e to the rt. So we will put this second possibility, which is not found yet, here. So d minus r, what is capital D by the way? Capital D is the derivative. It is the derivative operator. Let's take it as a time derivative. Normally, capital D's are used for position derivatives, but in this case we are interested in the time derivatives. So let capital D be the time derivative d by dt. So that we have d minus r squared is d minus r times d minus r. This operator is squared. So let me rewrite the first line. D minus r times d minus r and x2. What is x2? x2 is, let me forget this time dependence for the simplification of notation, v times e to the rt, and that has to be 0. So let's keep the first one and apply d first and then r on the parentheses. So this is d minus r, first one is waiting still. So d applied on this. So there's a product, and v is a function of time, it is not a number. So it has a time derivative, so let me call it v dot. Derivative of the first times the second, plus first one itself, derivative of the second, which is r times e to the rt, and that has to be 0. It's not finished yet because we also should multiply by r. Negative r times v e to the rt is equal to 0. And if you compare these two, they are the same. So plus vr e to the rt minus vr e to the rt cancel. So we only have this term. Now we have to apply this operator again. So d applied on this product will be derivative of the first. It was already first time derivative, now I do the second. V double dot e to the rt plus v dot r e to the rt, now this is finished, minus r times v dot e to the rt. That has to be 0. The same thing happens here. So these were the same, and these are the same, so that v dot r e to the rt is cancelled. And we have v double dot e to the rt is 0. So if you divide by e to the rt, v double dot is a 0. If you integrate once, you get v dot is a certain number. But if you integrate once more, v will be a times t plus b. But this b, for simplicity, b can be taken as 0, so we don't have to deal with this added term. And a can be taken as 1, so v of t is simply just the time t. So the second solution, then, the second independent solution is x2 of t, which is t times e to the rt. x1 was, remember, x1 was just e to the rt. Second is t times e to the rt for the simplest case. Therefore, the general solution is general solution for the critically damped case is x of t is an amplitude, not these a's and b's, but let me write it in the general form. A plus bt, okay, times e to the minus beta t. So this is the general solution for the critically damped case. It is important, the critically damped cases are relatively maybe more important than the others because of some applications. For instance, we use some measuring devices, galvanometers, ammeter, voltmeter, etc. Old type, not digital one, but some ammeter or voltmeter having a needle. Okay. For instance, we may use a certain, this is the scale, that means it's a voltmeter, and here is a needle. And for instance, this is the result expected at 3 volts. So you apply your voltmeter to a certain circuit, potential, you want to measure the potential difference across a resistor, for instance, and let's say it turns out to be 3 volts. But this system is a certain oscillating system. Therefore, it takes some time. If, for instance, remember that in the underdamped case or overdamped case, it takes a long time to reach the equilibrium. So this will make oscillations back and forth several times maybe, and then after a time of maybe 5 or 10 seconds, it will reach the equilibrium position and show you the expected value of the potential difference. However, the critically damped cases are the ones that reach equilibrium in the shortest time. Let's remember the picture where we plotted all of them. This was the critically damped case, T, and this reaches without making oscillation. It doesn't go to the other side of the horizontal axis. It doesn't make oscillations, unlike the underdamped case. But this reaches the equilibrium in the shortest time. Or for instance, some closure system, some doors. Okay, so a door, for instance, is open when you try to pass through, and if you come back and close it. But if it waits long enough, as in the case of overdamped case, for instance, that we will see, so for a long time the door will stay open. But we generally do not want such long waits. Therefore, we want the object, the door, the window, whatever the system, to reach equilibrium, to close as soon as possible. So for these purposes, the system should have a certain damping parameter, which is, let's say, omega 0 squared has to be equal to beta squared, such that we have a critically damped system, and this formula will be used for those cases. We also have the third type, which is the overdamped case. In the overdamped case, we said that omega 0 squared was less than beta squared, so that in the root we have a positive number. X of t was, in this case, e to the minus rt, beta t. X of t was e to the minus beta t, the damping part, a1 e to the omega 1t plus a2 e to the minus, maybe let's make omega 2 omega 2t, where omega 2 is defined as beta squared minus omega 0 squared. So the shape is a function, a graph that reaches 0, but it takes a longer time compared with the critically damped case. So for applications, this is not a good one. It can be used in some places, of course, but technologically or for practical purposes, critically damped cases are more important. And these are real explanations. However, in the first case, under damped case, there were i's here, remember? I omega 1, I omega 2, so that the I omega 1 minus I omega 1, so that they were imaginary explanations and they were oscillating on the one hand, but amplitude was getting less and less. In the critically damped case, there is no oscillation, and we only have A plus BT and just the real negative exponential. And then in the third one, we have, of course, the dropping term, but some exponentials. And these A1, A2, or AB, the other constants, can be found from the boundary conditions, initial conditions, etc. For instance, if you have a certain position at the beginning, and velocity maybe 0, maybe other values, velocity at the beginning, then you can find the coefficients A, B, or A1, A2, whatever needed. Let's also talk about the energy to some extent for such an oscillating system. So for an oscillating system, let's say x of t is a function, let's say a, for instance, cosine omega 0 t minus delta. Then x dot of t, which is the velocity, is a times an omega 0 coming from the inside, but cosine becomes minus sine, like this. And the energy is, remember, the kinetic energy plus potential energy can be written as the sum of these two terms. Kinetic energy is 1/2 mx dot squared, potential energy is 1/2 k times x squared. If you write them, for instance, in this form, 1/2 m square of this is a squared omega 0 squared sine squared omega 0 t minus delta, but plus 1/2 k times a squared cosine squared omega 0 minus delta. But what is omega 0? Remember, omega 0 was defined as k over m. So replace this omega 0 with k over m. So that m's will cancel, and we have the same term, 1/2 ka squared sine squared. So energy E will be 1/2 ka squared multiplied by cosine squared omega 0 t minus delta and sine squared omega 0 t minus delta. And we see that this is equal to 1, so the energy is just 1/2 ka squared, which is a constant. And A is the initial amplitude. If you at the beginning you, for instance, this is a spring. It is a spring, and assume there is a block at the tip of it. One end is fixed, the other end can be elongated or compressed. This is the normal length, unstretched length. at the beginning, if you elongate it by a distance a from equilibrium, and then leave it, assume there's no attenuation, no dropping in the magnitude, it will make oscillations back and forth, and the energy is constant, it is fixed. It is constant. And it depends only on the initial amplitude of oscillations and the force constant of the spring, K. Now another important thing is the phase diagram or phase space, phase plane. There are different, slightly different terms for that. Phase space, phase diagram, phase plane. Phase plane is a plot on a plane.